and I think move this into view slideshow. Sometimes it takes twice to go for some reason. Can you guys see my sidebar, or is that just me? I see it.
No, I can see it too.
Oh, you can see it. Okay, I'll move it over to the side then. Is that okay?
Yeah, from what I see, it's always been stuck on the side, and it didn't move around at all.
Okay, is it covering the slides?
Oh, no, not at all.
Okay. Okay, great. Well, we have John Field here today, and everybody knows John Field from the BANR project, so I won't do a big introduction, but thanks for sharing with us today about LCA in the BANR project.
All right, thanks a lot. So yeah, it's my pleasure to be here today and to be speaking to you guys about an overview of BANR lifecycle assessment activities. And I know that you guys had a presentation from John Sheehan here at CSU that was kind of basics and theory behind lifecycle assessment. So I'm going to try to skip over that stuff pretty briefly, just do a little bit of introduction, and then mostly focus in on some of the specifics that we're working on for the BANR project. But just a little bit of background on me. I'm a research scientist now at the Natural Resource Ecology Laboratory here at CSU. I finished up my PhD in the engineering program here last summer. And so I've been kind of a bit of a hybrid. My background's all in engineering, but as I got more into life cycle assessment for biofuels and bioenergy, I started doing more and more ecosystem type stuff, and I'll show you why in the course of this presentation. So today I'll give just a quick overview of some of the stuff that we're doing on the BANR project, a little bit of background first, then jumping into the specifics. And when I do a talk like this, I usually like to start off with my motivations and how I got into life cycle assessment. And so when I was an undergrad, I was a mechanical engineer, and after I finished my degree, I went and I worked in industry for a few years, and I worked in fuel cell research and development. And this was back in 2005 and through 2008 when the hydrogen economy was the big buzzword. And so Beth, can you advance to the next slide? And one more after that. All right. So yeah, so this, the hydrogen economy was kind of the buzzword of the day, and people were starting to realize that importing a lot of oil might be a problem. People were starting to get concerned about climate change, and the solution that a lot of people, including a lot of politicians, like the president at the time, the governor of California at the time, was fuel cells and the so-called hydrogen economy. And the idea there is that hydrogen can be used as a fuel. Fuel cell is a device kind of like a battery where you put hydrogen in and you get electricity out without any kind of emissions. And so the thought was we're all going to be driving around in fuel cell vehicles 10 years from now. They're not going to be polluting anything. We're not going to be importing oil from the Middle East, and everything is going to be great. And so I was very excited about this. I was very proud to be working in this industry. But a few years in, I read a book that really changed my outlook on it. It's this book, The Hype About Hydrogen, by Joe Romm, who is a Department of Energy scientist and part of an advisor in the Clinton administration. And one of the points he was making in his book, he was claiming that the whole hydrogen economy was a bit of a boondoggle. It was greenwashing, and his reasoning was that if you look at where hydrogen comes from in order to make these fuels. Oh, Beth, can you back it up one more? All right.
It's doing it on its own. I'm not doing it.
Oh, it's a mind of its own?
Yeah.
I'm not sure why it's doing that. You might have to fight it a little bit.
Tell me, like, if it goes and you don't want it to go, just tell me.
Okay. It'll be good motivation for me to speak more quickly. And anyway, so the point of this book was that if you look where hydrogen comes from, a lot of times it's generated from fossil fuels. And so in the end, you're not really getting away from fossil fuels. you're still encountering those upstream in your supply chain. You're still consuming those fuels. You're still producing a bunch of CO2 in order to make that hydrogen. Even to the extent that you can get hydrogen from other sources like solar or wind electricity, it's not a particularly efficient process. And so he made the point that, yeah, gee, we would be much better off taking that clean electricity that we have on the grid and keeping it on the grid and using it to displace coal. And so reading this, it took a lot of the wind out of my sails and really kind of soured me on the whole hydrogen economy thing. But it really did get me thinking about life cycle assessments. And so if you could go to the next slide. So life cycle assessment, or LCA, at the most basic level, it's the study of supply chains, right? It's the realization that in order to make a product, you have to have a whole bunch of other industrial inputs associated with that. For example, if you want to make ethanol, you're traditionally producing that in a biorefinery, a dry mill biorefinery in this case. And if you advance it one more, you'll see that there's a lot of inputs to that biorefinery. You have to have corn in order to convert the corn to ethanol. Your biorefinery probably takes some natural gas in order to run all the equipment there. And then you have to think about, okay, where does corn come from? Where does natural gas come from? If you look at corn production in the U.S., there's a whole bunch of fertilizer involved. There's diesel fuel that you need to run your tractor back and forth. And so the environmental impacts of making your ethanol, what's coming out of the process on the right side, is the sum of all these different arrows in red, all these different inputs and outputs associated with all of the different upstream processes in order to create the inputs to ethanol. So in order to understand the impacts of your ethanol, you have to understand the entire ethanol supply chain and all of the impacts associated with that. Okay, next slide. All right. And so bioenergy LCA is particularly interesting compared to other types of life cycle assessment because it's really inherently interdisciplinary. You have to have all kinds of people working together in order to really understand what's going on. And I tend to focus on the 3 E's, the engineers like me, the economists, and then the ecologists. And so the engineers, it's kind of easy to understand where they come in. They're the ones that are designing all these different supply chains and really understanding what the inputs and outputs look like, particularly for biofuels and advanced and second generation biofuels that maybe don't really exist at the moment at large scale. So we're still kind of guessing what those future industries are going to look like. And so if the engineers are the ones that are doing the process design and making predictions about, I think a future biorefinery might look like this, it might be this efficient, it might require this much cellulosic feedstock material to generate the fuel, it might require this much energy, et cetera, et cetera. And so in order to understand the full life cycle impacts, half or 2/3 of the effort is just defining what that supply chain looks like, doing all the process modeling, the process engineering. Economists, on the other hand, if you advance to the next slide, they have kind of a slightly different role in all of this. Back in 2008, somebody made the point that gee, you might have all kinds of indirect land use change issues associated with biofuel production. And what they mean by that, if you advance it one more, it's this idea that if you displace a lot of the crop production in the U.S., if all of a sudden you introduce a new demand for corn and other food crops, you start diverting material away from food markets. The U.S. potentially starts exporting less corn to world markets. And as a result, maybe people in Brazil and other places in the world are starting to produce more corn to make up for that shortfall in demand. And in a place like Brazil, in order to make more crops, you're potentially expanding your area of agriculture into some sensitive areas, like the Amazon and the surrounding ecosystems there. And that has a huge environmental footprint. That's not something that we want to be encouraging. And so even though this has nothing to do with the supply chain directly, this is not the kind of stuff that an engineer can really model or say much about. When you look at the big picture of these different supply chains, in some cases you get into these situations where maybe one supply chain kind of competes with or infringes on another supply chain, and you get into a situation where maybe you're robbing Peter to pay Paul, to the extent that land is limited and you start taking up additional land to make biofuels. Maybe you get some of these leakage effects or indirect effects that you don't want that start to erode the sustainability of the whole process. Next slide, please. So those are the engineers, those are the economists. Then the other question is ecologists, where do they come in? And for a long time, we treated biofuels as carbon neutral. The carbon in the fuel itself, the thought was that comes from a plant. The plant took that out of the atmosphere when it was doing photosynthesis. And so then when you take that plant material and you convert it to a fuel, and then you burn that fuel, that fuel emits CO2, right? All the carbon that was in that fuel goes back to the atmosphere in the form of CO2. But it was okay, right? Because that CO2 came out of the atmosphere originally in order to grow that plant, in order to make that fuel that you then burn. And so the thought is, okay, this is a closed, kind of a balanced cycle. That carbon is all neutral, and then we can just ignore it from our analysis. But when you really start thinking about this for different types of biofuels, as you see on the next slide here, it starts to become a little problematic. So when you start thinking about woody feedstocks, like we study for the BANR project here, so this is a lodgepole pine forest in northern Colorado that had a lot of beetle mortality. You can see in the background a lot of those trees are gray and dead, and all the needles have fallen off. If you think about the harvest in this situation, all of those trees that are coming down in the foreground of this picture, those, if they get converted to biofuels and bioenergy, and that fuel gets burned, all of that carbon that was in those trees is going to be back in the atmosphere in a matter of months, right? That's a pretty quick cycle to take that stuff down, to convert it, and then to consume that in a car or a truck or whatever else. Whereas all those trees in the background, all those dead guys that are standing up still there, if you think into the future, a year from now, most of those trees are still going to be there. They're still going to be standing there. They're going to be dead. They're not doing any photosynthesis, but they're still going to be there on the landscape. Even 5 years from now, a lot of them are still going to be there. Even 10 or 20 years ago, maybe they're all fallen over at this point, but those logs are still going to be there, at least partially, as they slowly decompose over time. And so as a result, in the short term, this isn't carbon neutral at all. It takes a long time for that forest to regrow, and it takes a long time for that dead material to decompose if you don't take it for bioenergy. And so that's something that the ecologists have to consider. Next slide, please. And so this brings us to the ecological disciplines of biogeochemistry or ecosystem ecology. All right, this is the study of the carbon cycle and the nitrogen cycle, and understanding how quickly plants grow, and then once they die, how quickly they decay, and how quickly there's decomposers and heterotrophs that cycle that carbon back into the atmosphere. And the speed of that growth and that death and that decay is going to tell us something about how sustainable our system is, and how much of a deficit we would introduce on the landscape, how much of a carbon deficit we would introduce if we start taking a lot of material out in order to make these biofuels and this bioenergy. All right, next slide, please. And thank you so much, Beth, for doing all the advancing there.
No
worries. All right. The other interesting thing is to think about in all this is this idea of carbon negative biofuels. And so this is the concept, before we talked about plants take CO2 out of the atmosphere when they do photosynthesis in order to build up their tissues. With bioenergy production, we take that carbon that's in these plant tissues, we convert that to various forms of energy, and then burn it and recycle it back to the atmosphere. But what if, in the course of doing that, we could divert some of that carbon into a more stable form? What if we can instead of sending it right back to the atmosphere, we can hold on to it? What if we can either, say, produce biochar as a co-product of our energy process, and take a fraction of the carbon that was in that biomass and put it in the ground and have it stay there for long periods of time? Or what if we're burning the biomass to produce electricity, what if we take all the exhaust that's going on our smokestack and we pump that underground and put that into geological storage? What happens then? Are we potentially taking some of that CO2, capturing it by plants, and then sticking it in the ground? Are we actually pumping CO2 out of the atmosphere at some rate? And so that's a really interesting question. Can you advance it, please? Yeah, so in that case, you have to think about, is it better to do that? Is it better to forego the biochar and make all the energy possible? One more, please. Or is it better, as you start to think about this, there's a lot of issues of timing that come up. You have to reconcile the idea of, making biofuels now and displacing fossil fuel emissions current day versus a forest that's maybe taking decades, multiple decades to regrow and recapture that carbon over time. Next one, please. And, the carbon negative angle in all this is really interesting, because when I first started working on my dissertation, that was a little bit of a pie in the sky idea. That was kind of a cool concept, but it was a little bit more science fiction than anything else. It was something fun to think about, but it wasn't clear if that was a real thing or not. But interestingly, over the last couple of years, we've gotten to the point where greenhouse gas emissions are so bad, and we're so slow in terms of reducing those emissions and slowing climate change down, that the people that are crunching the numbers are starting to warn us that, gee, even in the most optimistic scenarios of, deploying a lot of wind power and a lot of solar power and a lot of biofuels and things like this, we're at the point now where we're almost certainly going to overshoot. We're almost certainly that's going to be too little too late. And if we really want to stick within our climate change goals, if we really want to limit future climate change to below 2 degrees Celsius, we're almost going to have to do some of these negative emissions technologies, what's called carbon dioxide removal, at very large scales, because we're probably going to overshoot our emissions and then have to take some of that CO2 out of the atmosphere. And so this figure was from a paper a couple years back that was making this point. They show on the left side there, those are CO2 emissions over time. So there's good scenarios in blue and in green and yellow, where we're limiting our emissions, we're staying below our climate targets, and there's bad scenarios in gray and red, where we're just emitting a lot and we're getting a lot more climate change than anybody really wants. But they made the point that all of these scenarios that the Intergovernmental Panel on Climate Change, the UN agency that studies these things, all of those scenarios in the blue and the green and the yellow that turn out okay, where we avoid the worst of climate change, all of those are assuming that we're doing bioenergy with carbon capture and storage and these other negative emissions technologies at very, very large scale, to the tune of maybe 20% or 30% of all of our energy production are these carbon negative biofuels. So it was really surprising for me to fully realize that this idea that was a little bit science fiction when I first started in this area, all of a sudden is starting to become a necessity and something that we're really going to have to make work if we want to avoid the worst of climate change in the future. All right, next one, please. Okay, so to start off, we're going to talk a little bit about the BANR project here, the project scoping and stakeholder engagement, and kind of defining the problem and laying out the scope of work. Next one. So we started this process with a stakeholder webinar last fall in order to get feedback on our plans and our proposed methods. When you look at the standards associated with doing life cycle assessments, the goal and scope definition and then interpretation are very important pieces of the whole. So you're supposed to be engaging your stakeholders throughout your entire process as you design your study, as you implement your study, and as you generate and interpret your results, in order to make sure that you're studying the things that people are interested in, you're using methods that other people buy into, and everyone's kind of on the same page. And so we held this webinar last fall. We had participants from industry, other academic partners, including from the NARA project, our sister project, as well as some government agency folks to kind of give us some advice and some preliminary feedback. And next one, please. And so the proposed scenario, we tend to think of the problem in three pieces. There's beetle kill all over the western United States, over huge areas and very large quantities. And it comes in a variety of forms. So there's some areas where the best thing to do, the local land managers recognize that the best thing to do is just leave that beetle kill alone, right? It's in areas that are maybe ecologically sensitive, maybe they are in roadless areas and federally protected areas, areas that are too high a slope to get at that anyways, and those areas we can throw out of the analysis entirely. So advance it one more, please. So we're just going to chuck all those out of the analysis. There's plenty of beetle kill out there, though, that people are planning to go in. The landowners and land managers are going to go in, and they're going to take that down for a variety of different reasons, because they want to reduce fuel loading, because they want to protect trails and infrastructure from trees falling over, because they want to get the next stands of trees growing in. And in those cases, if there's going to be a harvest already producing timber and getting some of that material off the landscape, that tends to leave a lot of slash, a lot of branches and treetops and needles and things like that. Next, please. That typically is just piled up and burned on site. And so in those cases, the question is, can we come in and take some of that material that would otherwise be burned and doing something productive with it? There's a third category of land on the landscape, and that's areas where managers might want to go in and harvest and remove some of this beetle kill, but they can't at the moment because it's prohibitively expensive. But, however, when you consider bioenergy and doing something productive with this beetle kill, you get into a situation where maybe if you have additional revenue because you can sell some of this material to pool planets or to a power plant or something else, maybe that improves the overall economics, and maybe you can harvest some things that you couldn't harvest before. And so in that case, forward one more, please. In that case, what you're comparing to is not having a bunch of slash in a pile that you would otherwise be doing. You're actually harvesting in a landscape where you wouldn't have harvested before. And so that has a variety of things that you have to consider associated with it. The amount of carbon that's stored on that landscape, if you had just let that stuff stay in place and decompose versus removing it. There's different wildfire risks associated with it. And so it's a little bit of a separate assessment problem. And so if you advance to the next one, one more, please. The life cycle that we're thinking about here is shown on the top there. So this is a case of if you were going to harvest this material no matter what, on the left side you see, okay, we can either burn the slash piles that we end up with, or we could put it into a bioenergy production chain where we take that material, we forward it out of the woods, we chip it up, we transport it to a conversion facility. There, maybe we produce liquid biofuels out of it. Maybe if it's Cool Planet technology, we co-produce some biochar. And as a result, we displace some of the stuff that's going on the bottom of the panel, right? So we don't have a big pile of burning slash, and we're displacing some traditional or some conventional gasoline production, which involves exploring for oil in the Middle East or in Alaska or wherever else, and then a traditional biorefinery and end use in a vehicle. So those are kind of the two cases that we're comparing and contrasting against each other. But there's a bunch of different variations on this, as you see in the next slide. We don't want to focus solely on the cool planet process. We also want to consider alternate uses of biomass. So you might say, instead of giving the material to cool planet, maybe we're going to run it through a pellet mill, and we're going to co-fire that in a coal-fired power plant, and we're going to displace a little bit of coal use instead of a little bit of gasoline. Alternatively, on the next slide, we consider the case where, okay, maybe you wouldn't otherwise have biomass harvest in the first place. Maybe that was prohibitively expensive, but as a result of your bioenergy technology, maybe you get additional harvest, additional removal of beetle kill wood from the landscape that you wouldn't get otherwise. And so all of the downstream stuff is the same. You know, you're still considering biochar production and liquid fuel co-production. You're still displacing conventional gasoline. But on the upstream side, within the forest boundary, you have to think about, okay, the comparison is between doing nothing and allowing that stand to slowly regenerate naturally, you know, and having those dead trees slowly fall over and decompose over time, versus going in and removing all that biomass, co-producing some timber, and then kind of resetting that stand and getting back to that clear-cut situation that we saw in one of the earlier slides sooner rather than later. And so on the next slide, I think you just see, you can consider that same upstream stuff with the alternate downstream energy production as well. So on the next one, these are all the different scenarios that we're thinking about that we put before this webinar of interested stakeholders. We also talked to them about potential impact metrics. So what are the things that they want to know about? You know, we talk a lot about greenhouse gas emissions associated with biofuel production, but for any industrial process, there's a variety of other environmental impacts that you could talk about and that you could consider using the same life cycle assessment methods that we're doing for greenhouse gas emissions. So you could be thinking about local air pollution. You could be thinking about water consumption, water quality, and stream flow. All of these other impacts that you might be making better or you might be making worse with your particular technology compared to the alternative of conventional gasoline use or conventional coal use in the case of your alternate bioenergy pathways. And when we polled our stakeholders, it was very, very interesting because I was assuming that there was going to be a wide variety of interest in all these different impact metrics, and that was going to be tough for us because we didn't necessarily have the resources to hit all of these things. But if you advance it 2 more steps, so what we heard back, the feedback that we got was everyone was interested in greenhouse gas emissions and whether or not these fuels, these different technologies could be good for climate change. And then the other one that really stood out was wildfire risk. In this part of the country, you know, the forests are dry. We tend to have big wildfires getting bigger in area and more severe in intensity over time. And that's something that was really on everyone's mind. And so the marching orders that we got from this group, if you advance to the next slide, was focus on those greenhouse gas emissions, you know, looking at this beetle kill to biofuel and biochar. You know, is this good from a climate change perspective? How sensitive is our answer to various pieces of the puzzle, considering the supply chain, considering the ecosystem carbon response, considering how you do the greenhouse gas accounting. And then on the next slide, I'm going a little bit quick for time. What can we say about wildfire? You know, that was the big one that came up, and how does that interact with our ecosystem carbon modeling that we're already doing? For example, if we're taking a bunch of that dead material off the landscape, does that make us less vulnerable or equally vulnerable or more vulnerable to wildfires? Or does that result in less intensive wildfires than you might have had if you left more fuel on the landscape? And this is a really tough one to assess. We're actually still struggling with this a little bit as a group, trying to figure out exactly how much we can say about this issue. So this is definitely a work in progress. But if you advance to the next slide, I'll talk a little bit about the preliminary work so far. On the next one, we tend to divide the problem into these three different pieces. We're going to look at the supply chain, we're going to look at the ecosystem, and we're going to integrate those two pieces. So you can think about it going back to the 3 E's. You know, we're going to get the engineering view in that first box. We're going to look at the logistics associated with harvesting this material, taking it out of the woods, putting it into a bioenergy supply chain. And then we're going to look specifically at the Cool Planet Energy Systems technology to make biofuel and biochar. We're going to model their system and try to quantify how efficient that is, how much energy that takes, how much fuel we get out of that system, how much biochar we produce as a co-product. So that's the engineering side of things. And then on the flip side, the ecologist piece, we're going to look at how that ecosystem recovers after you go in and harvest and take that material out of the ecosystem versus how it recovers from the beetle kill if you leave all that dead stuff in place. And additionally, to the extent that we can, we're going to try to introduce this wildfire piece. Are these stands more or less susceptible to wildfire of lesser or greater intensity with and without harvest? And then I'm skipping over the biochar piece, but I understand you guys have interacted with a lot with the biochar group. And so that's kind of the carbon negative piece to the technology we're looking at. So if you're producing, if you're co-producing biochar, if 10 or 20% of the carbon that goes into your system comes out as biochar, and that's relatively stable once you use it as a soil amendment, how does that affect your overall balance? And then finally putting those two pieces together. So advancing to the next slide and looking at the supply chain detail, have you guys heard from Nate Anderson and the logistics team yet?
Yeah, I think we had a presentation by Nate.
Okay, perfect. So you guys are all experts then on the cool supply chain stuff that he does. So the challenge for us on the LCA team is to take the work that he's doing and integrate it into our models. And so, for example, you know, that group is looking at the different ways that you might get the extra biomass out of the woods and into a bioenergy supply chain. So looking whether it makes more sense to take that material and kind of chip it up in place where you harvest it, so actually getting the chipping equipment into the woods and then just hauling the chips out of the woods, versus if it makes more sense to harvest those trees whole, to drag them to a central place to remove the branches and the tops and the needles there, and then to chip it up and haul it away from there. And so they're out in the woods, you know, following the contractors around with stopwatches and trying to evaluate these different systems, these different ways of doing things, and trying to estimate what's most efficient, what costs the least, what's the most optimal way of doing things. And if you advance one more, the challenge for us then is to take the results of that and to put it into our models, right? And to understand, hey, if the optimal technology in our area takes a certain amount of diesel use in order to run your harvesters and run your chipping equipment and run your trucks, and you add all that together, you know, what's the footprint of diesel fuel use associated with each ton of chips that you could then use for bioenergy? We've done a little bit of preliminary number crunching so far. We've compared the numbers that Nate and his teammates have generated previously to some of the default numbers that are in the life cycle assessment tools that we tend to use. So GREET is a life cycle assessment tool that one of the national laboratories has put together, and it's a very commonly used one. And there have been various versions of that life cycle assessment software, and they've tried to make estimates of the greenhouse gas footprint and the diesel footprint associated with with harvesting waste biomass from these forest systems. And their estimates are, all over the place, and they've kind of evolved a little bit over time. Working with Nate and his guys, we can then make a more precise estimate or a more specific estimate to our systems in the Intermountain West here. And so instead of using the generic numbers from the GREET model, we can use their number of 1.7 or 1.8 gallons of diesel use per bone dry ton of biomass removed. So that's an example of what we do on the supply chain side. On the next slide, on the fuel conversion process, the question becomes how efficient is the Cool Planet process compared to some of the other hypothesized technologies that are out there, some of the things that are assumed in this GREET model. And so there, what we want to do is sit down and work with our industry partners and make a model of their system, make a model of the energy balance and the mass balance of that system, and really understand for a given mass, a given unit of feedstock, a given unit of chips that goes into their system, how much fuel do they make, how much biochar do they make, how much energy do they make versus how much is lost. And this diagram on the left there, that's from an analysis of a completely different system that I did a couple of years ago. But it kind of gets at the type of thing we're talking about here, where we look at for a given amount of energy that's coming in on the left side of that diagram in the form of feedstock, how does that get spread out? How much of that is lost in various sources versus how much output do you get for that amount of input? And if you advance it one more, you'll see a picture of this is the Cool Planet pilot facility located in Southern California. And the reason that we're doing this talk this week and not next week is because I'm going to be out there looking at this system next week, trying to make one of these models. So I'll be working with Darren, who many of you have met, our contact over at Cool Planet. And we're going to work with them to do one of these mass and energy balances for their system that we can then incorporate into our model. And it's a little bit of a delicate process because we have to be very sensitive to them. We can't divulge too much about the specifics of their system, right? Because that's sensitive for them. They don't want all their competitors in industry to know exactly what they're doing. So we do things at kind of a high level, so you can see, what the inputs versus what the outputs are, but not necessarily all the details that would be sensitive for them. So that's what we do on the conversion technology side. On the next side, we start to switch away from the engineering view and into this ecosystem view. And that's a case where we on the life cycle assessment team are working with the environmental impacts team. So the members of the BANR project that are actually out in the woods taking measurements in various beetle kill stands, trying to figure out what the implications of harvesting are. So they're doing a lot of before and after measurements in areas where there's active harvesting. So they'll go in and inventory how many trees there are, how many live ones, how many dead ones, what species, before a harvest occurs. And then 6 months or a year after that harvest, they'll go in and look at all of the seedlings that are starting to come back up in those various stands. We'll look at how many there are, what species there are, and then they'll try to model that into the future. They also do what are known as chronosequences, and that basically means going back to areas where they know there was a harvest, 5 years ago or 10 years ago or 20 years ago, and then looking at what those harvests look like today and comparing a bunch of different systems of different ages to try to get a sense of what a regrowth cycle looks like. So instead of looking at a single site over the course of 20 years, which would be a very, very long project, I think longer than USDA wants to fund, they look at a bunch of different sites where they know the history and they kind of put together a pseudo time series representative of an individual site. And if you advance it one more, what they can do from these various measurements is make estimates of how these these different forest stands recover if you leave them be after the beetle infestation versus if you harvest them and take all that excess material off the landscape. And if you advance it one more, so in addition to this, we have to think about biochar and wildfire, and I'll skip over that in the interest of time. On the next slide, you start to see aggregating that up to the landscape scale. So what the environmental impacts team is doing is a lot of plot scale stuff. What I and my colleagues on the life cycle assessment team are going to be doing is taking those individual results and trying to model them at the scale of a landscape and saying, okay, if we know what a single stand will do, what happens when we extrapolate that to 10 stands or 100 stands or 1,000 stands across a landscape? And what happens when we start to add in fire events? So what if we say, you know, we know the probability of a big stand replacing fire in a natural stand is 1 out of 100. And what if we know that reducing that extra fuel loading associated with the harvest reduces that fire frequency to, or that fire probability to 1 in 150, how do we start to aggregate all that together and really understand at the landscape scale what the carbon cycling implications of all that are? And so that's the type of modeling work that we're doing. I know that I'm running a little bit low on time, so I think I'll have Beth, if you don't mind advancing.
I think, yeah, I think you're okay. I mean, if you want to go another, 5 minutes, that's fine.
Okay. Well, if you don't mind.
But if you want to, yeah, tell me which slide.
Yeah, I'll maybe skip this one. We're getting kind of lost in the technical weeds here. Skip that one, and then we'll do the next one. Okay, so I'll speak a little bit about this one and the one right after that. And I think that'll be a nice kind of picture of how all this stuff adds up. And so this slide shows when you start to put all of these different pieces together, what it looks like. And so in the middle panel there, when you're thinking about traditional gasoline use, so conventional gasoline production and use in a motor vehicle, you tend to have emissions associated with producing that oil, getting it out of the ground in Saudi Arabia or Alaska or wherever, or Texas, wherever it happens to be, transporting it to a refinery, producing gasoline from it. There's a variety of greenhouse gas emissions associated with that. And then there's a whole bunch of greenhouse gas emissions associated with actually burning it in your vehicle. And so we're showing that in the middle plot in terms of tailpipe emissions and in terms of oil upstream emissions. So you have a certain climate impact associated with all those activities at a certain point in time. And as time goes on, the effects of those emissions are attenuated. If you look at the way CO2 cycles in the atmosphere, over time, some of it gets absorbed into the ocean, some of it gets absorbed into trees and vegetation in the biosphere, and some of it sticks around for very, very long time periods. And so if you start looking into the future, you know that for a set of emissions now associated with producing gasoline and then using that gasoline in your car, you get a spike of CO2 emissions that degrades and decays a little bit over time, but very slowly. So there's still lots of it left in the atmosphere after 100 years or 200 years or 300 years. That's how we do the climate impacts associated with that industrial activity, that gasoline use in conventional vehicles. What we compare that to on the top panel there is this crazy BANR bioenergy scheme where we're going to harvest a bunch of trees, we're going to make a bunch of biofuels. And so on the one hand, when you're doing that, you have all kinds of energy use associated with harvesting that material, with you using diesel fuel to run a harvester and a chipper and a grinder and a truck to get the chips out. You have energy use at your biorefinery in order to convert that material into biofuels. in all of these things, and those are shown in the purple and the blue and the orange there. And in addition to that, you're taking all these trees off the landscape, right? You're going from that dead material that would stay there for a certain amount of time, and then you're releasing all that in the short term. And so those are the emissions that you see in green there, the positive emissions. But then balanced against that, after a year or 2 or 5 or 10 years, you start to have that forest regrow and take a lot of CO2 out of the atmosphere through photosynthesis, through growing trees that are replacing that stand that you harvested from the landscape. And so in the biofuel case, you have a bunch of negative emissions right below the zero line associated with that forest regrowth. And those tend over time to offset a lot of the impacts associated with making your biofuel in the first place. So you have a big initial impact, maybe even bigger than in your gasoline reference case in that middle panel, but then over the course of 10 and 20 and 30 and 40 years, a lot of that impact is offset and reduced by the regrowth of your forest. And so when you look at those two things, when you compare the bioenergy case on the top versus the conventional gasoline case on the bottom, what you see in that bottom panel is the ratio of the one to the other. So anything that's one, a ratio of 1 means they're equally bad for climate. A ratio of more than 1 means the bioenergy case is worse for climate. And a ratio of less than 1 means the bioenergy case is better for climate. And so what we can see when we put all these different processes together and look at how things change over time is that there's a period of maybe 15 or 20 years where the forest hasn't quite regrown. In terms of the atmospheric emissions, the amount of CO2 that's in the atmosphere, you're actually slightly worse having done the biofuels in the short term. But then after 20 years, that forest is really cranking, really regrowing, and sucking up all that extra CO2, whereas that's not the case for your traditional gasoline use, your conventional gasoline production. And so after 20 years or so, your biofuel is better. It beats your conventional case, and into the future, it's significantly better. So those are the kind of trade-offs that we look at when we put everything together. And on the next and final slide, you'll see the sensitivity of our results. Our model, if you start changing parameters and try to get a sense of what matters the most to this answer, what matters the most to the overall climate impact, the things in green are factors associated with our ecosystem model. So things like how quickly the stand regrows, if you get a change in fire frequency or intensity associated with your harvest. And the things in red are associated with the engineering side. So how much fuel you're getting out of the Cool Planet process, how much energy use, how much diesel you have to use to get stock out of the forest, things like that. And what you see is that, unfortunately, you really have to consider both of these pieces in the assessment. You can't really take a shortcut and focus on the one or the other because both of them matter and matter a lot. And so that's why we've kind of taken the broad view. We've gotten our engineers working with our ecologists, and we've tried to put those two pieces together to really get a broad, holistic view of what's going on in these systems. So I think I've said plenty there. Thanks a lot for listening, and I'd love to try to answer any questions that you guys might have.
Thanks, John. We also already have a couple questions from Logan in the sidebar, if you can see those, unless you read them.
Ooh, I can't see them.
Okay. Can you hear me?
I can hear you, yeah.
Okay. First, Logan asked, why does the CO2 impact begin to go back up after 50 years or so? CO2 emission impacts continue, but regrowth slows? That's on.
Yeah, so let's see here. Yeah, there's a little bit of a minimum, and then yeah, there you go. A minimum around 50 years or a little bit before, and then it actually slides backwards a little bit. And that's really specific to the dynamics of how these stands regrow. What happens is if you get all of the stands are young and regrowing at kind of the same age, the way we modeled wildfire, the wildfire frequency is a little bit less there. And it's only when the stands get very mature and a little bit older that you really start getting the wildfire risk back to kind of the baseline case. So that's kind of a secondary effect associated with wildfire risk. That's something that, as I mentioned before, it's really tough to model, and so that's definitely something that we're still trying to figure out and still see how real that is.
Okay, and thank you. And Logan has another question. He says, would it be correct to say your model estimates that after about 20 years, the forest biofuels have roughly 60% less emissions than fossil fuels?
60% less emission. Yeah. I think the way to say it is, yeah, after 20, 25 years, the amount of additional CO2 in the atmosphere as a result of doing biofuel is only 60% of what it would have been had you done an equivalent amount of conventional gasoline. After 30 years, after 50 years, after 60 years, that ratio is changing over time because the regrowth dynamics of the forest are different than the dynamics in the fossil system.
Does that help, Logan? Yes, thanks. Any other questions for John?
You have a question. Does the model take into account like a perpetual cycle of forest management? Like you'd go in year after year after year and harvest different parts of the forest?
That's an excellent question. And at the moment, it's a little bit in between. We consider that for all of the different forest stands across the landscape, you wouldn't harvest all of them in year one. You'd kind of spread that out over 5 or 10 or 15 years. And that's why there's a little bit of a slow ramp up to that green curve, the positive green curve in the top panel here. But what we're not yet considering is, 100 years from now or 150 years from now, if this whole thing repeats, and if you get into kind of a standard cycle of you're going to do this every 100 years or every 150 years. And I think that question is a great one because it gets at a larger issue, a larger truth in these systems that a significant issue all across the region is the history of management. The fact that 100 years ago or 120 years ago, all of these areas were clear-cut when the mines and the railroads first came through. And then for most of the time since then, we've been doing forest fire suppression and putting out all of the natural fires that would otherwise be reshaping what the forest looks like. And so we're currently at a state at the moment where things look very different from what they would be naturally. You have everything that's the same age, and you have a lot more biomass on the landscape than is really natural. And so the really interesting thing about bioenergy, in my opinion, is, yeah, maybe you could use it kind of as a proxy for forest fire, right? Because we're going to keep suppressing fire so we don't have home loss and we don't have people killed in these wildfires. But can you do bioenergy to kind of mimic the natural shaping of the forest that you ought to be getting from wildfires, but that you're not getting anymore when you put them out every year? That's a great question.
Thanks, John. Other questions
Sure
for
thing.
John?
All right, can you hear me?
Yes.
This is Pat. All right, I guess my question, I do a similar assignment with my high school kids where I give them a bunch of different alternative fuels from, biochar, not biochar, but cellulosic, ethanol. We do corn ethanol, just talk about all these different biofuels, and the depth at which you're going at is quite a bit for the type of students that I deal with. If you were going to limit it to 4 or 5 major topics or areas to focus on, what areas would you talk about? Would we go, I certainly talk about the engineering part of it, not so much the economics. Well, a little bit of economics and then a little bit of the ecologists. I just kind of trying to look at, where to focus my attention and their attention so that we can, get a better idea of where to go.
Sure. Yeah. No, that's another good question. And I've taught a little bit of this at the college level here, and what I like to focus on with those, when I do an introductory lecture on this, I think that corn ethanol is a really interesting example, and it's kind of an example of how not to do things. There's a lot of sustainability issues associated with corn ethanol, but it's a little bit easier to understand and conceptualize and talk about than some of these more esoteric accounting issues. You can really talk about, is it a good idea to be producing a lot of corn on the landscape, considering that corn requires a lot of fertilizer? Is that a good idea? When you put down a lot of fertilizer, that has implications for water quality and the Gulf of Mexico dead zone and things like that. I feel like corn ethanol is kind of a nice example, a cautionary example of how things can go wrong in all of this. So that's the one that I like to use.
I guess my thing is I start with corn ethanol, I'll give them that as kind of an example, and then we go, and then I give them, kind of a choice to get to choose from, like 7 or other, choices from algal to, all these kind of, I guess in theory, theoretical models that, that are kind of out there that people have these ideas, kind of like your hydrogen model that you talked about before, these kind of things that, that are kind of, I don't even know, experimental, I guess, in nature,
Right.
And so, and that's kind of how we get into the beetle kill kind of thing, cellulosic, because it's just kind of cutting edge or, theoretical model that we're trying to figure out if it's going to actually work or not.
Absolutely.
Corn ethanol has been around for a while, and we kind of know what's going on there, I think.
Yeah. Well, another example that you might give them is the first round of cellulosic ethanol plants is starting to open up in the U.S. So there's 2 or 3 commercial scale facilities that have opened up in the last year that instead of using corn are using corn stover, so the leftovers after you take the corn grain. And so there's 2 of those in Iowa and 1 of those in Kansas at the moment. And those are kind of new and kind of experimental at this point. They're commercial scale, so they ought to be to the point the technology theoretically is mature enough that it can start to compete with the corn ethanol common. But it's still brand new, so we'll know in the next year or 2 if those folks are still in business or not, if that's a good idea. But yeah, I kind of like that as a progression, to start with the corn ethanol that has some drawbacks that you can talk about and explore, and then maybe segue into, there are 2 or 3 new facilities on the horizon. What do you think about these? Do these get rid of some of the issues that the corn ethanol facilities have? Are they likely to be better or worse? Do you think that they're going to do well, or do you think they're going to go out of business? That kind of discussion.
Thank you.
Sure.
Thanks, John. Well, I think we're at a little after 5:30, so if anyone else, final parting thoughts? That was great. We really appreciate your taking the time to share that with us, and it's kind of cool to see it in the BANR context for sure.
Oh, absolutely. Thank you so much.
Thanks, John.
All right.
Okay. Bye, everybody.